This is definitely what I wanted to say. So that last video accidentally cut off a little bit early, and that was not intentional. I'm sorry. So this will be set 6 of the midterm practice. And I'm actually just going to jump back in onto the page I was already in and start from there. Below are a range and standard deviation for a set. Okay? Here's the range rule of thumb. Remember, that's the rule that says that empirically we expect to be able to have 2 standard deviations around the mean. So in other words, we expect to be able to fit 4 standard deviations from the minimum to the maximum. So and there's one more way you could say that. You could say that the usual minimum would be 2 standard deviations subtracted from the mean, and the usual maximum would be 2 standard deviations added to the mean. So I know I'm saying it fast because I'm not teaching it, I'm just reviewing it, but the PowerPoints are in chapter 3 are a good place to review this. Alright, and compared to the standard deviation, does the range rule of thumb produce an acceptable approximation? Okay, well let's do that part first. So normally we would take the range and we would divide it by 4. And our range this time turned out to be 2 9400ths. We divide that by 4 and we get 0.735. That does not look so close. Okay, is this an acceptable approximation? Well, what are they determining acceptable? Suppose a researcher deems the approximation acceptable if it has an error less than 15%. So let's find out how much of a difference there is here. So we'll take this minus that, and I know that's going to be negative. I can just ignore that and divide by what I started with. And that is a 21% difference. Or if I would have calculated the difference, the percentage difference from the original, the actual standard deviation, 892 thousandths minus 735 thousandths, and divided by the 892 thousandths. I'm still above 15%. So in either case, I'm noticing that the difference is too big. So is it acceptable? No and no, because the error of the range rule of thumb's approximation is greater. Yep. Number 22. A certain group of test subjects had pulse rates with a mean of 79 1/10 beats per minute and a standard deviation of 10 9/10 beats per minute. Would it be unusual for one of the test subjects to have pulse rates of 70.9? Okay, in other words, they're wondering if this falls in the usual range. And that, again, actually goes back to the range rule of thumb and goes back to how we did this. We took the range and divided by 4. So it's just like, it's an alteration of that, essentially. They derive from the same original rule. So we're going to take the standard deviation right here, which is 10 9/10, and we're going to double it. In fact, I'll just go ahead and mark that number down. I'll save that one. 21 8/10, and I'm going to subtract it from the mean, and that will be my usual min, and I'm going to add it to the mean, and that will be my usual max. So 79.1 minus, memory recall, 57.3, let me put the other one in, 21.8. Let's see, I messed something up there. Oh, I didn't hit enter. Good to pay attention to what I'm doing. Okay, so 100.9. Alright, so is 70.9 beats per minute a usual pulse rate for this set of data? Sure. I mean, look, it was pretty close to the mean, and by close I meant because my spread was moving by almost 11 points. So one standard deviation is going to take me 11 points below and 11 points above. In fact, you know, we are going to start drawing the pictures a lot more often. Let me go ahead and draw the picture for this. So what I would have been thinking of would be a distribution. It may not be bell-shaped, but I start out by having it look like that. I put the mean right here in the middle, and in a bell-shaped distribution, we expect the mode and the median and the mean to all be the same. You know, this perfect theoretical version. And then we're going to go over one standard deviation to the right, over two standard deviations. I'm denoting these by S. For sample standard deviations, that's because I already started by using a sample mean notation there. You know, I could have started with using a population mean, and then I would have denoted by moving this over 1 sigma, the population standard deviation. Either way, so you know, I'm moving 2 over this way. This would be my usual maximum, and if I were to move the other direction in my distribution, you know, minus s minus 2 s's, or minus sigma minus 2 sigmas, this would be my usual minimum, right? And we could see ahead of time that if this was 79.1, we're definitely going to fit 70 point, what was the number again? 70.9 in there, within the usual 4 standard deviations around the mean. In other words, we say that this is within 2 standard deviations, is what we're really referring to as the plus or minus. Okay, so choice is all the way down here at the bottom. No, it wouldn't be unusual because it's between the usual max and the usual min values. It's sometimes you got to keep yourself really busy paying attention between whether they asked if it was unusual or whether they asked if it was usual when you go to say the yes or no part. But I'm sure you guys already know that. You've been doing the homework for a while. All right, we're finally hitting chapter 4 here with number 23. If A denotes some event, what does A bar denote? Now this is capital A. Well, actually, good time to go to your symbols page and see if you can remember what some of these things are. P of A is the probability of event A. So that kind of reminds us where we were using the event notation. P of A vertical bar B means that P of A given the B has already happened. So they word it as probability of an event A assuming that the event B has already occurred. It's a different calculation, especially depending on if they're independent or dependent samples. Alright, way up here at the top. It's funny that it's up here, but it's just another reason why you want to get to know all of these pages very well. A bar is the complement of A. So that it is on the symbols page. It's probably also on, well, I know it's also on the review page. There's that review page. That's the calculator review. We have several of those. Alright, here's this review page. So, yeah, right. So we also have it under these. Alright, so what does A bar denote? Event A bar denotes the complement of A, meaning that A bar and A share some but not all outcomes. No, they don't share any outcomes. What are you talking about? Event A bar is always unusual, whatever that means. Events A and A bar share all outcomes. Event A bar denotes the complement of event A, meaning that A consists of all outcomes in which event A does not occur. True. And that's the proper wording for it. So, you know, if event A was picking a redheaded stepchild, then event A bar would be not picking a redheaded stepchild. And that shouldn't be confused with picking a dark-haired, you know, tall, dark, and handsome, beautiful stepchild. Whatever. By the way, if there's any redheads out there, don't take offense. I've got a lot of redheads in my family, and I used to be more of a redhead. Okay, anyway. If the probability of event is this, the numerical value, right? So this is the 0 through 1 scale that we use. What's the value of this? Well, it would be 1 minus that. So, in other words, 9 minus 9, which is 0, 9 minus 9, which is 0, and then 10 minus the last one, which is 1. There's the little trick for you, by the way. So you just do 9 minus 9 minus, and then 10 minus, and whatever the last digit is. Alright, if the probability of the event is this much, is the complement of the event unusual? Sure it is, because there's the numerical value for the complement, and that is less than 5%, so yes, it's unusual. You toss a coin randomly, select a number from 0 to 9. What's the probability of getting tails and selecting a 7? I think this is the last thing we have time for on this set. So let me draw this out actually. And we should remember this is actually not that bad because we're tossing a coin, okay, so one coin, and then we're randomly selecting a number 0 through 9. Now, there's 10 digits there, but what's good about this is that these are independent events, right? They're disjoint here, or mutually exclusive, if you remember that phrase. So I'm going to draw the tree diagram for the possibilities we have here. So when we flip the coin, it could land on heads or tails, and then depending on what happens, we do the next part of the event, which is to randomly select. Think of it like rolling a 10-sided die or something. We roll the die and it lands on a 1, a 2, a 3, a 4, a 5, and so on. Similarly down here, if it had started out by flipping a tails, it could have landed on a 1, 2, a 3, or 4, and So what I'm doing here is I'm describing for myself the sample space. And in fact, I'll relist the sample space in another way. The first possibility described from that tree diagram I just made is flipping a heads and landing on a 1. Flipping ahead and landing on a 2, having heads, landing 3, until you exhaust all the digits for, actually I should have put a 0 in there. I'll put the 0 at the end then. So typically you start with 0 here, but I'm going to have 0 down here at the last possibility. So I exhausted all the ones for when I flipped ahead, and then I could flip tails and land on a 1, tails land on a 2, and so on. Tails land on a 9, tails land on 0. Okay, so how many possibilities are there altogether here is really the initial question, because this is my sample space. This is how big n is. And there are 10 for the heads and 10 for the tails. So I can essentially just use the multiplication rule. Remember, it's 2 of this part and 2 ways here and 10 ways here. So 2 times 10, or 20 total possible different ways that we can have this event occur. Okay, and then our specific question is the probability of getting what we want, tails, and selecting a 7. Okay, so we calculate our probability. I'll call our event A also, by the number of ways that we can have our event occur divided by the total number of possible outcomes. The number of ways for our event to occur is 1. There's only one way, right? And that would be somewhere in this range right here, where we landed on a tail and chose the number 7. One way that that's going to happen out of 20 possible simple events. So 1/20th. Believe me, it could have been a lot worse. So 1/20th, what's that one going to be? There we go. So I didn't hit submit earlier when I did the last set. So let's see if I blew any of those, because I've made a couple mistakes, which is good. I want you to see what anyone would do if they were doing the test, especially if they're doing it at 12:26 a.m. making mistakes. All right, so here's another partial. 2/3 credit. I missed 1/3. What did I make? I must have made a mistake here. Wow, that shouldn't have been. Thought I pulled those numbers right off the page. So stats, summary stats, columns, and since I'm only looking at the second one, I'll just take the more recent winners. It wasn't a big enough mistake to make me change my conceptual answer at the end there, my final conclusion there, but I wanted the standard deviation divided by the mean, so I took those two numbers. And I probably could have done this part in in StatCrunch. No, I guess I just rounded wrong, because I should have gotten 6 3/3800%, and I put down 6 3/3300%, and even though it gives me tolerance for the right answer, I still have that wrong. So good to know. Now it's still wrong, and at this point I've lost, I think, a whole percent now, so I don't want to keep that up.